All right. 11 people. PA4 took its toll. 12 people. All right, so next week we're doing PA5 presentations starting on Monday. If the class is this small, that's not going to take too much time. But we're also going to spend part of next week doing some review, talking about the final, maybe getting a lead into object-oriented programming for spring. So we've got miscellaneous things we'll be doing next week. So this is kind of our last week for new material, depending on how next week pans out. So what I want to do is talk about PA4 briefly, talk about SLPs briefly, because your upload is due theoretically a minute ago, but it's open until 5 p.m. So if you haven't turned it in, you can still do it. I want to go through some PA4 code. I want to talk about tree balancing some more. We'll talk about PA5, and then I want to talk about more aspects of dynamic programming, get into some other problems we can solve with dynamic programming. We'll revisit the Oracle of Bacon and talk about breadth-first traversals in that context. And then depending on how much time we have, we may get into Huffman trees and we may get into decision trees. So we'll just sort of play with tree space for a while. So that's the basic agenda for today for the rest of this week. Any questions before we start in on some of that? Yeah?
There's no planned ODPs for this week.
I may do some ODPs, but I'm thinking probably not. But if I get a brainstorm and say this would be a great ODP, then I may post one or two. But I don't have any planned right now, and there's nothing posted right now. All right, so PA4, first of all. PA4 is graded. I think people did a fantastic job on PA4. Even if your code wasn't doing everything that it was supposed to do, right? I went in, I looked at source code, and I think people have got the idea of recursion pretty well down, which is really one of the keys in this course, right, is to get comfortable with recursion. And height function, search function, right, those are all recursive, and it looks like that's working well for people. So that's a definite win. Tree algorithms, right, most of the tree algorithms, the idea of inserting in the left or right subtree and taking the root and replacing. I saw that in most code. Searching the left or right subtree and returning the value from that. So I think people are in good shape, right? I think you've got the idea of trees and manipulating them. So deletion, is always like this big can of worms, and if your deletion doesn't work, that's not a crisis. Breadth-first traversal is tricky because it's built on top of another data structure, which is a queue, which is built on top of another data structure, which is a linked list. So it's sort of 3 layers there, and just getting that lined up within the time budget is tricky sometimes. But I saw really good code, so I was really happy with that. So biggest issues that I saw people running into. The first is obviously delete, right? And there's edge cases with edge cases. But there's one thing I saw a lot of people doing, and I haven't figured out why so many people did this. But when we talked about deletion, right? Deleting, if you're not deleting the root, you just recurse, right? If you're deleting the root of the tree, the algorithm that I tried to be really consistent about is find the largest thing in the left subtree, replace the root with that, right? And the only exception to that is if there is no left subtree. If you only have a right subtree, then and only then you're allowed to simply move the root down to the root of that right subtree, right? Any other case, if you've got stuff on the left, find the largest thing in the left, replace the root. But probably about a quarter of the class did the following. If you had a tree like this, what should you do? Find the largest thing in the left subtree, that's a 15, make that the root. So you should end up with that. But about a quarter of the class said, oh, there's nothing on the right, I'm just going to move the root to here, and they came up with this tree. It's a valid way to delete a root from a tree, right? But it's not consistent with the algorithm we were working on. So if you got a comment that said your delete algorithm is using something different from what we went over in class -5, right? That's probably what was going on, or something similar. Because there's lots of ways that you can delete a root of a tree. We could delete by replacing the root with the smallest thing in the right subtree. And in the world of tree deletion, that's absolutely valid. It's as valid as anything else. It's just not the algorithm we were using. So that popped up a few times. The other exception was in tree balancing. So is that a balanced tree? Right, it's balanced trees should be very, very full towards the top. They should fill in at the top before you go down too deep. This is the second worst tree we could imagine. This is probably the worst, right, or that. But this is just two of those really horrible trees sitting together. This is absolutely not balanced. But a lot of the balance checks came back and said this is balanced, because all it was doing was checking the height of the left subtree and the height of the right subtree, saying they're within 1, right? That's one of 3 criteria. For a tree T to be balanced, 3 things have to be true. Left and right subtrees need similar heights, and the left subtree has to be balanced, and the right subtree has to be balanced. So it's recursive. And if you don't do those last 2 steps, then this ends up looking balanced. So that was the second most common error. Breadth first traversal, some people just didn't put it in, and you figured this out by now already, but if you don't have something working quite right and it breaks your whole program, don't put it in. Leave the code in, but comment it out. Put something in the submission comments saying, you know, I got most of this coded, but it's not linked in. So some people just didn't call the breadth first traversal, which is fine. But if you were calling BFS and it wasn't working, mostly what I saw was part of the nodes just wouldn't appear, right? And that's something going wrong in the insert. Maybe you're inserting the left subtree or the right subtree instead of both, or your test condition for whether to insert is off somehow, or you got 1 equals instead of 2 or something, but nothing major. All right. Let me talk about the SLP. So I posted an announcement this morning, or last night, this morning. So 224, you turned in a poster. It was a different poster, okay? 224, you're starting your SLP usually, and the goal of what you did in fall quarter was really kind of refining the problem that you wanted to work on. So I want to make some kind of device to let me write on paper, but take what I write and get transferred into a computer. So maybe I'm going to do that with a camera, maybe I'm going to have a transmitter in my pen, maybe I'm going to have special paper that picks up pressure, maybe I'm going to use magic unicorn dust or something. So you come up with different ideas, right, that you need to dig into, and you spend fall quarter doing some research, okay, so research analysis, proposed solutions, what are the potential applications. It's really an exploratory phase, okay? And then at the end of fall, you present what you found so far, and then in winter term, you continue to refine and develop those ideas. So, so problem definition may be a little more specific, or it may be the same. Competitive analysis, you're looking at what else is out there, what the current solutions are, comparing that to yours, and so on and so forth, and then details about your solution. So I came up with a way to track the motion of this pen, but it also picks up my hand, and I'm trying some things to deal with that, including wearing a black glove, right, or whatever. So it's a further refinement of the ideas. So your poster should not look the same as it did in 224, because hopefully you've made some progress, right? And progress doesn't mean now I've got a working prototype and I'm ready to sell it and get rich. It may be that you tried 5 different things and none of them worked. That's progress, okay? That's Edison's, 9,000 ways to not build a light bulb thing. And that's all stuff that can go into the poster, keeping in mind it's just one page. So in 223, right, throughout spring quarter, hopefully you're developing towards some kind of more refined version of your system, either a working prototype or a more detailed specification of the solution or something like that. Your final submission for 223 is actually a formal report. Okay, so it's a written document as a PDF file. Could be 20, 30, 50 pages long, okay, that basically spells out all the details of your project from start to finish, everything about the implementation of it, code, circuit diagrams, test results, all sorts of things like that, okay. That's a full-on formal presentation. Like if somebody was giving you $5 million to do this, this would be what you would give them in exchange for your $5 million. Okay, so that's a step beyond the single poster. Yeah?
Does the cutoff all be on the PDF, or can it be like on the post? Can there be just like a link to a PDF or something?
You mean for 223?
Yeah.
Yeah, you can put in links. Because sometimes it's like tons of code. All right, so you got basic idea what you're looking for to turn in like 12 minutes ago? So the upload area is open until 5 o'clock. So 5 p.m. tonight I'll download everything that's been uploaded and it'll get sent off to the printer, and then you'll have posters next week. So make sure you get that in before 5. And that's 50 points. The presentation is 50 points, so half of your SLP grade is getting this thing uploaded. So make sure you do that. All right, questions on that? All right. So you want to talk about PA5. Let's talk about PA5 first, and then let's go back and look at some PA4 code and talk more about balancing. But let's discuss PA5 a little more. Do you have specific questions, or just kind of going over the whole thing?
Yeah.
So so you know what the knapsack problem is, right? You have a bag with a certain capacity. You have an inventory of items with values and weights. How do you get the maximum value out of the bag? Let's look at an example. So let's say item A. So here's item, here's weight, and here's value. So item A has a weight of 1 and is worth, let's say $4. Item B has a weight of 2 and is worth $20. Item C has a weight of 3 and is worth $35. And let's say your capacity is 4 pounds. So our goal is to find the maximum value that we can get out of a 4-pound bag from this inventory of items. Now this inventory is going to change from problem to problem. This is what's sitting inside a file called knapsack.data. So one of the first things your program has to do is open this file, ingest this information, save it somehow. So so that it can do what we're about to do, which is find the max value for whatever capacity you ask for. So how do we do this? We can't do a greedy algorithm, right? This is the most valuable item by weight. It's worth almost $12 a pound. But if we put this in our bag, we get $35. We only have 1 pound left over, which is item A. That's worth $4. We get $39 out of our bag. If we put in 2 of item B, we'd get $40 out, even though item B is only worth $10 a pound. Loading up on that is more valuable than using this more valuable item C. So greedy algorithm doesn't work here. So how do we find the max value of 4? Well, here's the algorithm we're going to use. We're going to say there's 3 possibilities. So max value of 4 equals the largest of the following 3 possibilities. It could be that we put in item A, which gets us $4 in value and leaves us 4 minus 1 pounds of capacity. And what's the most we can get out of that remaining 3 pounds capacity? Well, that's what our MV function will tell us. So if we put item A in our bag, the maximum value we can get out from a 4-pound bag is 4 plus max value of 3. If instead we put item B in our bag, that's worth $20. And it leaves us a capacity of 4 minus 2 is 2 pounds. So whatever the max value is for 2 pounds, that's going to be our max value. And if instead we put item C in, we get $35 in value, and we're left with a capacity of 4 minus 3 is 1 pound. And that's all we got to do is calculate these 3, see what the largest is, that's our answer. And calculating these 3 is easy because we've already got an MV function. That's where we're in the middle of writing. And once you put the curly brace on it, right, then we can call it. So you make a loop, you loop through your items, and for each item you calculate the value of that item plus MV of your capacity minus the weight of that item. You do that across your entire inventory and take your largest value. That's your answer. So we're going to have to make a recursive call to MV3. And MV3 is the largest of what? So what are the possibilities for MV3?
Let's wait again.
Okay, so we could put item C in, which gets us $35, and then how much do we have left over in our capacity?
0.
Yeah, so max val of 0. Or what else could we do?
Could we not just like calculate the value per weight and then try and add in the item with the most value per weight?
Yeah, you can do that, but if we do that, this is worth $4 a pound. This is worth $10 a pound. This is worth $11.6 per pound. So C is our most valuable item. So that would suggest put in item C, which leaves us 1 pound, so put in item A also. Right? And that gets you a value of $39. That's not your best solution, though. Because your best solution is to put in 2 of these less valuable items B. That'll get you $40. Right? So what you're suggesting, that's what we call a greedy algorithm. And in some cases, that gets you an optimal solution. For this problem, it doesn't, which is why it's a trickier problem. So how else could we extract value from a bag that holds 3 pounds? This is the solution when we put in item C. What are the other possibilities?
20 and 4.
Yeah, so we could put in item B, which gets us $20. And how much capacity does that leave us with? 1. Or we could put in item 1, which gets us $4 and leaves us a max val of whatever we can get out of a 2-pound bag. So here we're going to have to calculate max val of 2. So that's the largest of, well, how can we possibly get some value out of a 2-pound bag? What are the things we can do?
2.
Yeah, can we put item C in our bag? Right, we can't because it weighs more than our capacity, so we don't consider the case where we're putting in item C. But we could put in item B, so we get $20 plus, and then we've used up our whole 2 pounds of capacity, so there's no space left. Or we could put in item 1 for $4, and that leaves us a capacity of 1. And so now we need to calculate max val of 1.
And that's easy because it's just A.
Yeah, we can't fit item C, we can't fit item B, so it's the largest of, if we put in item A, which is $4 plus max val of 0. So max val 0, we're going to hardwire to be 0. If your bag has a capacity of 0, you can't get any value out of it. So this is 4 plus 0 equals 4. So max val 1 is equal to 4. So we can come back from this recursive call to max val 1. This is 4 plus 4, which is 8. Max val of 0 is 0, so this is 20 plus 0, which is 20. So max val 2 is the largest of 20 or 8. Looks like max val 2 is 20. And here, when we want max val 2, if we're not doing dynamic programming, we're going to have to go through these calculations again and these calculations. With dynamic programming, we got our green pen to write down the values of these as we calculate them. So now when I say 4 plus max val 2, I know that's 4 plus 20, which is 24. 20 plus max val 1 is 20 plus 4, which is 24. And 35 plus max val 0 is 35 plus 0, which is 35. So what's max val 3? 35. So here we've got 35 plus max val 1, which is 4, which is 39. Here we've got 20 plus max val 2, which is 20, which is 40. And here we've got 4 plus max val 3, 35. That's equal to 39. So what's max val 4? 40, and we're done. Unless that was a recursive call we made in a problem that was looking for max val 100, in which case we'd return this and it would continue through other layers. So this is what your algorithm will end up doing, right? But it handles this recursive business, right? Your only job is to say max val n is the largest of, right? First value plus max val n minus 1, 20 plus max val n minus 2, 35 plus max val n minus 3, or whatever the values and weights are in your inventory. So if you get this right, it's beautiful and it's easy. It's when it's not quite right that it can drive you a little crazy. All right, other questions on that?
How do you figure out what you're putting in the bag?
Ah.
Max value.
Yeah, so that's a little trickier. So this max val function is just taking an integer capacity and returning an integer max value. What you probably want to do is return a structure. So here's just a suggestion. So struct solution, integer value, integer item count, 128. So my solution is going to have two pieces to it. It's going to have an integer, which is actually what the maximum value was that we got back. But I'm also going to return an array of 128 integers, which says how many of each item do I have in order to get that particular value. So it's not just the best value you can get, but it's also how you choose ingredients to get that maximum value. So in your recursive calculation of max val, we're going to say, okay, what's the largest? This, or this? And we're going to discover this is how I got my largest value. So as you're looping through and you're keeping track of the largest value, you also need to know which item corresponded to that. Okay, it corresponded to B, which was item index 1, right? Gave me my max value. So take the inventory of items that gave me this particular max value and increment the count corresponding to this item by 1. So if this gave me my best solution, I'd take the inventory of items that gave me this max value and I'd increment item bracket 0. Because that's what this corresponds to. If this gives me my total max value, take the inventory of items I got from here and increment the count of item 1. If this gives me my max value, take the inventory of items I get from here and increment the count for item 2. And now when I return my inventory of items for max val 4, it's got the correct count of each item to get me whatever the max value was. Does that make sense? So if we did an example with this, it would be really uninteresting because capacity is so small. But just imagine, instead of just writing down here, you also write down how many of each item. And then you adjust that count on each of these based on which max val you used. And like I say, that works best kind of as an add-on afterwards. Just leave yourself some time because you have to change the structure of max val a little to somehow pass back this item count. And you cannot make that global. Okay? People try to do that sometimes and it will always bite you because this has got to be local to your call to max val. Right? Otherwise subsequent calls will clobber it. So you got to somehow pass it back from your max val function. Does that help?
Yeah.
Okay. And the question came up on how to read the knapsack file, so let me go ahead and talk about that. So we did some code last period. So you open your knapsack file with an fopen call, right? So it returns an object of uppercase file star. Okay, so file star, file pointer, it's FP. So call fopen, give it the name of the file you're opening, which is knapsack.data, and give it a R in double quotes that says I want to open this for reading. And then you can use FP instead of stdin when you say fgets. So I can say fgets, there's a character array, length of the array, and instead of standard in, I'm reading from FP, that'll read from the file. And as long as the line is less than 128 characters, whatever it reads up to the new line will go into this character array called string. And then here, just as test code, we're printing out the value of string with a %s, and I'm also keeping track of how many lines we read. So we got a lines variable and we just bump it up. And when fgets returns null, it means you've hit the end of the file. So at that point I can close my file by saying fclose fp, and I'll print out the total number of lines that it ingested. Right, so if I run it on my current knapsack file, which has 4 lines, each line is, just another line from the file. Knows the total number of lines is 4, so you're going to save that and use that when you do your for loops to iterate through your items. Every line ends with a new line when you fgets, so you can deal with that however. And then this string variable, I could use that as an argument to scanf. And if you scan %d, %d, %s, it'll pick apart that line into 2 integers and a string. And so you can parse it out like that. Make sure scanf returns 3. That tells you if the file's corrupt or not. And then save those in some arrays, and then you're good to go. Make sense? Yeah.
We gotta check the file pointer for null, right?
Yeah, check the file pointer for null, because if knapsack.data doesn't exist or it's not readable, FP will be null and then your fgets would seg fault. All right, cool. So let's run through some PA4 code. So make files are looking pretty good. Okay, so almost everybody included a make file. Make files are happiest when you're compiling things in pieces. So I only had two pieces to my code, tree.c and q.c. Most people had more. So I have separate recipes for building each of my object files, my .o files, and then one recipe for my main program, which I just glom all my object files together. And then the clean one if I want to get rid of the results of making, so I can do a fresh make. So that's my make file, right, which everything's up to date. So the Q code was really just PA3 with a small change to it. So whereas the Q's in PA3 returned integers, I decided to return a pointer to a struct node. So my include file, my struct node has left and right pointers and a data value, and then I typedef uppercase node to be a pointer to node. And a Q node has a data piece, which is a pointer to a tree node, and then a next piece which points to a Q node, so that's a linked list, and then it has a tail pointer that we talked about in PA3, which is entirely optional. So the Q code, not a whole lot of changes, right? Add takes, instead of an int data, it takes a node data. And remove, instead of returning an int, returns a node. But nothing really changes anywhere in the actual code. When I malloc, I set the data to null. For my sentinel, that's totally optional. And when I add, ultimately, where do I set the data? Right here, right? I set the data piece to whatever I pass into it. But that's the only change, is that instead of int, I said node. The code is pretty much the same other than that. So Q code, not terribly exciting. So I defined three constants: node left right node for traversing. So I only wrote one traverse function, and I pass it an argument to say how I want it to traverse. That's just laziness in typing. So empty tree, the root should just be null. You can make an init tree function that returns null. I just set root equal to null in this case. Not totally an abstract data type anymore if I do that, but that's okay. So the standard parsing loop, and we've seen this multiple times now, use fgets to read an input. I usually scan for an integer first, because if I scan for a %c, it's always going to succeed, right? So see if there's an integer. If it is, we're trying to insert a number. Search, make sure it's not already in the tree, and then call your insert. And every time that you use insert, you have to take the return value from insert, reassign that to your root. Okay, that's the only way you can go from an empty tree to a non-empty tree. If they didn't type in a number because the scanf failed, then we're assuming they have a command, so just switch on the first character. If it's an X, let's call the examine function to see the tree, question mark gives me a usage, and so on and so forth. If I'm expecting something like S number, once I know I've got an S, use scanf again, see if it's S followed by an integer. If that returns 1, that's what you've got. If it doesn't return 1, you got an S, but you didn't have an integer following it. So, same thing for delete. and then Q, just call your memory release function. Anything else, say print a question mark for help. And then at the end of your loop, so if you hit Control D, it exits the loop, and then I just release the memory, and you're done. And we'll skip the delete function for now. So insert, if the tree is null, just make a new node and return that. Otherwise, either insert on the left and replace the left subtree, or insert on the right and replace the right subtree. And I saw this in most people's code, so that's good. New node. So malloc space for a node, struct node in this case because I don't want a pointer. Set the data to the value, and then I set left and right to be null. Now if you don't do that, Valgrind will complain. And if you get to the end of Valgrind and it says no memory leaks, you got full credit for freeing memory. But if you got 500 error messages while your program was running, good chance you weren't doing something like this. You weren't initializing your nulls to actually be null, and it's warning you about that. And it's good practice to get rid of all those warnings and errors from Valgrind, even if you don't have memory leaks, right? Because it's something that you're doing that's not totally clean, and you want to make sure you have these habits.
Problematic.
Yeah, it could be potentially problematic, maybe on a different system. So my traversal code, I call traverse. I give it a flag saying what kind of traversal I want to do, NLR, LNR, etc. So it's one set of code. If the root's null, there's nothing to do. Otherwise, if we're doing pre-order, I print out the root data. Then we traverse the left subtree. If we're doing in order, then I print the root data there. Traverse the right subtree, and if we're doing post-order, print the data after that. So that's just some code reuse. Print data deals with the comma foolishness, so initializes the flag to 0 up top, and then if the flag is set, I won't print the comma the first time, but then I clear it. So it prints a comma before each number except the first. And when I call traverse, all it does is set that flag saying this is the new traverse, and then it calls the actual traverse function. I didn't take off a point if you had a trailing comma. All right, so examining a root, that's just a bunch of calls to all my other functions. So do my 3 traverses, do the breadth first traversal, print out the height, print out whether it's balanced. So that's like the easiest function to write because it doesn't do anything. It's just a bunch of print statements and function calls. It's all the machinery underneath there. Search was one that was a little tricky in some cases. So if the root's null, so I return null if it's not found. I don't know why I did that instead of a 0 or a 1. If the root's null, your data is not found. If the root equals the data you're looking for, then we found it. Otherwise, what you want to do is search either the left or the right subtree, but you got to return the value from that call to search. In a lot of cases, people did the recursive call to search but didn't do anything with the return value, and then they just returned at the end. Sometimes that will work because sometimes the last thing that returned a value will still be the thing that's on the stack that ends up being passed back to the caller. So it may actually work successfully in some cases, but you want to make sure, since we need to return a value, return the value that search gave you. Sorry? Yeah, so height's coming up. So usage is straightforward. Release is this post order traversal, so release the left and right subtrees and then free the root. So those releases are recursive. Freeing the root is just plain old free. Breadth first traversal, so again the queue, we seed it by initializing the root, which is actually a node, and then remove the head. If it's null, we're done. Otherwise, print out a comma, unless the thing we just removed is the root of the original tree, in which case we don't want a comma in the beginning. Print out the node's data, and then if the left is not null, add that to the queue, same on the right. And when we're done, print out a new line and then free the memory in the queue. All right, so height of a tree. If the root's null, the height's -1. That's a definition, and it also is an edge case, base case for our recursion. Otherwise, find the height of the left and right subtree, add 1, and return whichever is larger. So if H1 is the largest, this is going to return H1, otherwise H2. So this is the pseudocode, right? Return 1 plus the maximum of the left height and the right height. Okay. Yeah, if you do the recursion, it's takes almost nothing. If you do it non-recursively, you can traverse the tree and save the depth at each point in the global, and then whatever the largest depth was, that's your height. But this one's does the work for you. Okay, balance. So again, balance, you need to have 3 properties satisfied. Either the root is null, that's automatically balanced, or find the height of the left and the right. Look at the absolute value of their difference. So that's what D is. This is just a homebrew version of that. If the difference in height is bigger than 1, it's not balanced. Otherwise, see if the left subtree is balanced. If it's not, the tree is not balanced. If the height's within 1 and the left subtree is balanced, you still have to check, is the right subtree balanced? And if that's not, tree's not balanced. If it gets through all of these checks, if the distance between the heights is less than or equal to 1, if the left tree is balanced and the right tree is balanced, then your tree is balanced, you can return a 1. So I finished grading PA4s like 6 or 7 o'clock last night. And I started Saturday morning. That's pretty much what I did this weekend. So I rewarded myself by letting myself write some code last night. So I decided to write the code to do balancing of a tree. And so I have another version of this. Which does balances. It was fun. I was really looking forward to this, so it wasn't as spontaneous as it sounds. So remember, when you did this on the board, the idea was you add something to your tree, you do an insert, and then you work your way up and you check to see if there's a node with a balance factor of 2 or minus 2. So balance factor is height of the left subtree minus height of the right subtree. So you calculate that as you go up, and if you find a 2 or a minus 2, you look at the child, and if it's minus 1, you've got this case. If it's 0 or 1, you've got this case, and so on. And then you make these adjustments. You say, okay, well, here's the thing that's unbalanced. We're not going to touch the right, but the left we're going to replace with the left's left child. And that thing's right child is going to become the old node's left child, and so on and so forth, right? And if you end up in this one, then you've got to do another rotation to get to the balanced case. But if your balance factor was minus 2 and the child on the right had a balance factor of 0 or minus 1, you can go straight to the balanced. So the first thing is, you don't have to do this business of starting with the node you inserted and working your way up and checking the balance factor all the way up to the root. That happens kind of automatically for you because the way we insert is recursive. So when we say insert something, we're going to say, okay, it's smaller than the root, so we're going to insert into this tree. It's bigger than that, so we're going to insert into this tree. Eventually, we're going to insert a leaf node. And if we check to see if that's unbalanced, right, it's going to be fine because it's just a single node. But when we return from our recursive call, remember what we've done was we inserted into a bigger tree to the right of this node, so now we're going to check that node's balance factor. And when we return from that recursive insert call, we were inside a call which said insert into the left subtree of this node and replace the left subtree with that new subtree. And now we can check the balance factor of the root of this tree. So if we just check the balance factor every time that we recursively do an insert, we'll de facto be searching all the way up the tree from the node we inserted up to the root. So we don't have to make a separate loop. All we have to do is, in these two cases, if we insert to the left, insert into the left subtree, replace the left subtree, and then, starting at the root of this tree that we were past, call this function adjust, which will check the balance factors and make whatever rotations are needed. And the same thing if we insert on the right, go ahead and do your insert, and then see if you have to adjust that point. And if it's some point higher up that's unbalanced now, eventually when we return this root, right, we'll be inside this part of the code, and we'll try to do an adjustment on our parent. So that'll work its way up, and that's kind of magical. So let's look briefly at the tree adjustment code. So first thing is calculating the balance factor. It's 2 lines of code. If the root's null, our tree is balanced, because the left and right subtrees have heights -1 because they're null. Otherwise, find the height of the left subtree, subtract the height of the right subtree. That's the balance factor, so you just return that. And I already got a height function written, so this was painless to write. And then here's the adjustment code. So if the root's null, tree can't be unbalanced. We don't have to do anything, so just return the root. Otherwise, check to see, for example, if the balance factor of the root is 2 and the balance factor of the left child is -1, we need to do this funny adjustment, which I call left-right. So if balance factor of the root is 2 and balance factor of the left child is -1, do the left-right adjustment on the root, save that in root. And so our 4 cases are coded up here. And if we're in a case like this, or if we're in this case and we do that adjustment, it turns it into this case. So after we've done that first if statement, all we have to do is say, is the balance factor 2? And that tells us either we were in this case to start, or we were in that case and we did a rotation and now we're in the left-left case. So the second statement is just if the balance factor is 2, do your left-left adjustment on the root. And then the same pair of statements on the right, and then return the new root. Okay, so here's where it got fun. So here's the left-right case, and this is just straight out of, the Wikipedia description of how to do these rotations. So left-right case, we're calling our root node 5, so N5. Left child is N3, right child is D, left child of 3 is A, etc., right? So as we discussed in class, I made a bunch of temporary pointers, initialized them to null, set N5 to the root that we're starting with. D should be N5's right child, so say D equals N5 right. Node 3, N3 should be N5's left child, so say N3 equals N5 arrow left. So this is more of that code that kind of writes itself, right? You just write some code to assign each of these nodes to one of our temporary variables. Now I got a little paranoid here, so before I set A to be N3's left, I made sure N3 is not null. And if that's the case, set A to N3 left, set N4 to N3 right. So that sets up these 2 variables. And then if N4 is not null, set B to N4's left, C to N4's right. So that sets up these. And then what's the adjustment we want to make? Well, the root's still going to be N5, N5's right is still going to be D, but N5's left should change to be node 4. So N5 left equals N4. And if N4 is not null, I want N4's left to be node 3. So if N4 is not null, N4 left is N3 and N4 right is C. And then if N3 is not null, I want N3 to pick up B on the right. And that's what that does. And node 3's left child is still A, same as before, so I don't need to do that. And then I return N5, that's the new root. And you do the same thing for the left-left case, and then for the right-left case, and then for the right-right case, and you're done. And it actually works, which I will admit I was completely surprised by. But that totally works. And then for deletion, it's similar, and I was getting tired at this point. So I don't claim that this is an efficient way, but for delete, basically, every time that I change the root, I just call adjust. So delete on the right, set new root equal to the new right subtree, and then I call adjust on it, and delete seems to work also. So this is worthless by itself, right? This is not code that tells you anything. Okay, this is code you write and the computer reads it. We don't usually go back and read this. This is how we think about tree rotation, right? This is just a translation of this paper into code that the computer can understand, right? But you never want to put that on your note sheet and hope that you can get an answer on your exam from this set of code, right? You want this on your note sheet, and you want experience with turning this into that. And if you can do that, then you're golden, right? So, anyway, so that was fun. All right, so tomorrow, bring questions on PA5. We'll talk about red-black trees, which is a different approach to balancing. And then we're going to go back to dynamic programming, look at some other applications of that concept. All right, so I'll see you tomorrow, or in a half hour.